This antenna is nothing more than a 6-foot copper pipe, a handful of sharpened wires, a single diode, and a metal stake driven into the ground. It has no moving parts, burns no fuel, and needs no sunlight or wind to begin producing electricity. Yet for less than $25 in materials, it can harvest electrical energy from the atmosphere 24 hours a day. The average American household spent nearly $1,900 on electricity last year, yet almost nobody has ever heard of a device like this. Over the next few minutes, I'll show you how it works, why the science behind it has been measured for over a century, and why researchers are once again exploring atmospheric electricity after decades of being overlooked. We'll look at the history behind the technology, from Nikola Tesla's early experiments to modern university research, before examining how people are building these systems themselves for less than the cost of a family dinner. But before we get to the antenna, you need to understand something more important. Once you see how electricity actually reaches your home, you'll understand why even small breakthroughs in energy collection matter. Electricity itself isn't especially expensive to produce. Delivering it is. Every unit of power generated at a power plant travels through hundreds of miles of transmission lines, substations, transformers, and neighborhood distribution networks before reaching your wall outlet. Along the way, between 8 and 15% of that energy is lost as heat before anyone can use it. You're paying for electricity that never even reaches your home. At the same time, much of the electrical grid is decades old and requires constant maintenance just to keep operating. Whether your electricity comes from coal, natural gas, nuclear power, hydroelectric dams, or renewable energy, it all depends on the same aging delivery system. Now compare that with something completely different. Above your head, every second of every day, the Earth's atmosphere naturally maintains an electrical potential between the ground and the ionosphere. Unlike a battery, it never needs charging. Unlike a generator, it never shuts off. And unlike solar panels, it works whether the sun is shining or not. That doesn't mean a simple antenna can power your entire house. At least not today. This is where many videos become misleading. Atmospheric antennas are not replacing the electrical grid tomorrow, and they won't run your air conditioner or refrigerator. Most DIY systems produce only tiny amounts of electricity, enough to slowly charge batteries, power sensors, or run small electronics continuously. But that's exactly why scientists are paying attention. The challenge has never been proving the electricity exists. The challenge is learning how to collect enough of it efficiently to make it useful. For more than a century, researchers have measured the Earth's atmospheric electric field. NASA has studied it, universities teach it, atmospheric physicists rely on it every day. The question has always been whether that naturally occurring electrical potential can be harvested in a practical way. Recent research suggests the answer may be changing. The device itself is remarkably simple. It begins with a vertical metal conductor, usually copper or aluminum. The higher it's mounted, the larger the electrical potential difference between the antenna and the ground. At the top sits a sharpened point or a cluster of thin wires. Those sharp tips concentrate the surrounding electric field, allowing electrical charge to transfer more easily from the atmosphere onto the metal. It's the same basic principle used by lightning rods. The collected charge then travels through a diode. Think of the diode as a one-way valve. Atmospheric electricity naturally fluctuates, but the diode forces the current to flow in only one direction, making it much easier to collect. From there, the electricity enters a capacitor. A capacitor doesn't create energy, it stores it. Imagine placing a bucket outside during a light rain. Each drop seems insignificant, but given enough time, the bucket fills. The capacitor works exactly the same way, collecting tiny amounts of charge until enough energy has accumulated to power a small device. The final component is the ground connection. A metal grounding rod driven into moist soil completes the circuit and allows current to continue flowing. Without that return path, nothing happens. That's the entire system. A metal antenna, a diode, a capacitor, and a grounding rod. Every component is inexpensive and easy to find, which naturally raises the question, if the design is this simple, why have so few people ever heard about it? The answer begins high above the earth. Every day, roughly 40,000 thunderstorms occur somewhere on the planet. Together, they continually move electrical charge into the upper atmosphere, creating what scientists call the global atmospheric electrical circuit. High above the Earth's surface lies the ionosphere, a conductive layer carrying an electrical potential of roughly 250,000 to 300,000 volts relative to the ground. That enormous voltage difference doesn't appear only during storms, it's present all the time. Near the Earth's surface, this creates a measurable electric field of roughly 100 to 300 volts for every meter of height. Scientists have measured it for generations. It's documented in atmospheric physics textbooks and confirmed by organizations including NASA. This isn't fringe science or internet mythology. It's a well-understood property of our atmosphere. The challenge isn't proving the energy exists. The challenge is finding practical ways to collect it. More than a century ago, one inventor believed exactly that was possible. His name was Nikola Tesla. Tesla is best known for alternating current and wireless power, but one of his lesser-known ideas focused on harvesting electricity already present in the atmosphere. In 1901, he filed U.S. Patent 685,957, titled Apparatus for the Utilization of Radiant Energy. His concept described an elevated metal conductor connected to a storage device and the Earth itself. As electrical charge accumulated, it could be stored and later discharged to perform useful work. Tesla wasn't describing perpetual motion or unlimited free energy. He believed the atmosphere contained usable electrical energy that could be collected under the right conditions. Whether his design could ever produce significant power remains debated, but the science behind atmospheric electricity itself was already well understood. Tesla was simply trying to make practical use of it. His larger vision eventually became Wardenclyffe Tower, designed to transmit power wirelessly across long distances. Early funding came from financier J.P. Morgan, but as the project's ambitions expanded, financial support disappeared and the tower was never completed. Over time, centralized electrical grids became the dominant model for delivering electricity, while Tesla's atmospheric ideas largely faded into history. But they didn't disappear completely. Decades later, another scientist quietly demonstrated that atmospheric electricity could do more than simply accumulate inside a capacitor. His name was Oleg Yefimenko, a physicist at West Virginia University who spent years experimenting with electrostatic motors powered directly by atmospheric charge. His setup was surprisingly simple: a tall antenna, a collection system, and a ground connection. Instead of charging a battery, the collected energy powered a specially designed electrostatic motor. It wasn't powerful, producing only a tiny fraction of a horsepower, but that wasn't the point. The motor ran continuously with no fuel, no batteries, and no external power source. His experiments were carefully documented and later published in his book Electrostatic Motors, proving that atmospheric electricity could perform measurable work under the right conditions. The problem was scale. Collecting tiny amounts of energy isn't the same as powering a home. For decades, that limitation kept atmospheric electricity on the fringe, while engineers focused on technologies capable of producing far larger amounts of power. Solar panels became cheaper, wind turbines became larger, and lithium batteries improved dramatically. Atmospheric harvesting remained mostly an academic curiosity. That changed in 2020 when researchers at the University of Massachusetts Amherst introduced a completely different approach. Instead of using tall antennas, they developed a device called AirGene that generated electricity from moisture in the air using microscopic pores. The first prototypes produced only tiny amounts of electricity, but they operated continuously without sunlight, wind, or moving parts. 3 years later, the same research team demonstrated that the effect wasn't limited to one specialized material. According to their findings, almost any material containing nanopores below a certain size could potentially harvest electricity from atmospheric humidity. Suddenly, atmospheric energy harvesting wasn't just one unusual experiment. It had become an entirely new area of renewable energy research. The outputs are still extremely small, and nobody is claiming you'll disconnect your home from the grid anytime soon. But researchers have stopped asking whether atmospheric electricity can be harvested at all. They're now asking how efficiently it can be scaled. That's a completely different conversation. Outside university laboratories, hobbyists have been reaching similar conclusions for years. Across electronics forums and YouTube channels, Builders regularly document atmospheric antennas producing measurable voltages in fair weather. Some report a few hundred millivolts, while others observe higher outputs as humidity increases or storms approach. Several have successfully maintained trickle charges on small batteries, powered weather stations, or operated environmental sensors using nothing more than elevated copper antennas and proper grounding. None of these projects produce unlimited electricity, and none power entire homes, but together they demonstrate something important. The atmosphere really does provide measurable electrical energy. So why hasn't atmospheric electricity become another major renewable industry? The answer is probably less dramatic than many people think. It's not that the technology has been deliberately hidden, it's that our entire electrical system was built around a completely different model. Utilities generate electricity at centralized facilities, transmit it through power lines, and charge customers based on how much passes through a meter. Every regulation, safety code, tax incentive, financing model, and an inspection process assumes electricity is delivered that way. Atmospheric harvesting doesn't fit neatly into those categories. There are no standardized residential systems, no widely accepted installation codes, and almost no commercial manufacturers producing certified atmospheric energy harvesters. Without those pieces, widespread adoption becomes extremely difficult, even if the underlying science is legitimate. That doesn't mean atmospheric harvesting will replace solar panels or wind turbines. It simply means researchers are exploring an energy source that has existed above our heads the entire time. If you decide to build one yourself, you'll quickly discover just how simple the hardware really is. The heart of the system is a vertical copper or aluminum antenna mounted as high as possible. Height generally matters far more than thickness because increasing the distance between the antenna and the ground increases the available electrical potential. At the top, builders usually attach several sharpened copper wires known as corona points. These concentrate the surrounding electric field, allowing atmospheric charge to transfer more efficiently onto the metal. The collected charge travels through a diode, which acts like a one-way valve, preventing the current from constantly reversing direction. From there, it flows into one or more capacitors, where the energy slowly accumulates until enough has been stored to power a small load. Finally, a copper-clad grounding rod driven into moist soil completes the circuit. In many cases, improving the quality of the ground connection has a greater effect than changing almost any other component. Altogether, the parts are inexpensive. Copper pipe, a few pieces of wire, a diode, several capacitors, insulated cable, and a grounding rod typically cost somewhere between $30 and $50. That's dramatically cheaper than virtually every other renewable energy system available today. Of course, low cost doesn't mean high output. This is where many online videos become misleading. Some claim these antennas can power entire homes or eliminate electric bills overnight. Current evidence simply doesn't support those claims. Under normal conditions, atmospheric antennas generate very small amounts of power. They're excellent educational projects and can slowly charge capacitors, maintain small batteries, or operate extremely low power electronics, but they aren't replacing your electrical panel. That's because the challenge isn't the atmosphere itself. The atmosphere already contains an enormous electrical potential. The challenge is converting enough of that potential into useful current efficiently. That's exactly what modern researchers are trying to solve. Imagine if future buildings could quietly harvest electricity every hour of every day. Instead of relying on a single antenna, roofs, windows, paint, or even concrete could become part of the collection system. That idea is still experimental, but it's no longer science fiction. Researchers are actively exploring materials capable of generating electricity from humidity, nanoscale structures that improve charge collection, and surfaces that work continuously without sunlight, moving parts, or fuel. Whether those technologies ever reach commercial scale remains uncertain, but the direction of the research is becoming increasingly clear. The goal isn't replacing every existing energy source. It's adding another one. Unlike solar panels, atmospheric harvesting doesn't stop when the sun goes down. Unlike wind turbines, it doesn't depend on moving air. Instead, it relies on electrical processes that are already taking place naturally in the atmosphere done 24 hours a day. That's what makes it fundamentally different from almost every renewable technology we use today. Of course, there are important limitations. Output varies depending on humidity, altitude, air quality, and local weather conditions. Two identical antennas installed in different locations may produce noticeably different results. These systems also require patience. They don't generate large bursts of electricity but collect tiny amounts continuously over long periods. And perhaps most importantly, safety can never be ignored. A tall metal antenna can also act as a lightning rod. Atmospheric electricity under fair weather conditions is gentle, but lightning is an entirely different phenomenon, capable of releasing billions of joules of energy in an instant. Anyone experimenting with these systems should never install or test them during thunderstorms and should always use proper grounding and lightning protection. So where does atmospheric electricity go from here? The honest answer is that nobody knows. History has shown that many technologies spend decades in laboratories before suddenly becoming practical. Solar panels existed for decades before falling in price enough for widespread adoption. Home battery systems were once considered unrealistic, yet today millions of homeowners use them. Electric vehicles followed a similar path. Progress in energy technology often appears slow until one breakthrough changes everything. Atmospheric harvesting may or may not follow that same trajectory. Today's systems produce only small amounts of electricity, but researchers continue finding new ways to improve efficiency. Every year brings better materials, better manufacturing techniques, and a deeper understanding of how these natural electrical processes work. Even if atmospheric electricity never powers entire homes, it could still become valuable for low-power electronics, remote sensors, environmental monitoring, or future building materials capable of generating their own electricity. The important thing is separating established science from exaggerated claims. The Earth's atmosphere does maintain a measurable electrical field. That has been understood for generations. Scientists have repeatedly confirmed the electrical potential between the Earth's surface and the ionosphere. What's still uncertain is how efficiently that energy can be converted into useful power. Claims that a simple backyard antenna can replace the electrical grid aren't supported by current evidence, but dismissing atmospheric electricity entirely ignores a growing body of legitimate scientific research exploring its potential. Sometimes the most interesting technologies aren't the ones that dominate today's headlines. They're the ones quietly developing in laboratories while most people aren't paying attention. Atmospheric electricity has existed for as long as our planet has had an atmosphere. The question isn't whether it's there. The question is whether modern engineering can finally unlock more of it. For now, these systems remain fascinating experiments that demonstrate a very real scientific phenomenon. A few pieces of copper, a diode, several capacitors, and a grounding rod are enough to show that the atmosphere above your home is electrically active every second of every day. The amount of energy may be small, but every major technology starts somewhere. Before solar, panels covered rooftops. They powered calculators. Before electric cars became mainstream, they were considered impractical curiosities. Innovation rarely happens overnight. So here's the question. If atmospheric electricity eventually became efficient enough to power part of your home, would you trust it? Or would you still rather rely entirely on the electrical grid you've always known? Let me know your thoughts in the comments below. And if you enjoy exploring overlooked energy technologies backed by real science instead of internet myths, consider subscribing. Because the next breakthrough in energy may not come from digging deeper underground. It might already be floating in the air above us.